All right, let's move on then. So now we'll have the rest of the class is dealing with going backwards. We spent all this time trying to take the derivative. Now we want to spend time looking at the reverse process, taking the antiderivative. So instead of knowing the function and trying to find the derivative, now you'll know the derivative and you want to find the function. You say, well, why should I care? Why should I have to go backwards? We don't get the y until chapter 5, but it'll be necessary, though, to do. The third part of calculus, there's limits, there's derivatives, and the third part of calculus is integrals. And this process of finding the antiderivative, we'll find out in chapter 5, is exactly that. So we'll start off simple with just polynomials. Since taking polynomial derivatives is rather simple, then taking polynomial antiderivatives should be rather simple. And then we'll get to more difficult antiderivatives. And so, what about if you have, so before we were given a function trying to find its derivative, now we're given a derivative, we're trying to find the function. What function has 8 as its derivative? 8x. Very good. But also, you can add to that any number you want. And so we say any number you want, we call it generically C. It's a random constant. Take the derivative of that function, you will get 8. Okay? Great. So if you have a constant, you get an x on it. That's just from intuition. From what we know about going forwards, we can quickly go backwards in that case. But polynomials are made up of x to powers, not just constants. And so, in general, if you have x to a power as your derivative, we know that, well, going forward, let's go with the going forward. If I have a function that is x cubed, the derivative is 3x squared. So the derivative is 1 degree less than the function. So this derivative here is 1 degree less than the function. So if I want to go backwards to find the function, I have to bump the degree up by 1. If I'm looking at the derivative and I want the function, I know that I have to add 1 to the exponent. But to take care of this constant that's in front, I need to divide by it. So it's not there anymore. And so the power rule in reverse is this. Add 1 to the exponent and divide by exactly the same thing. Take the x to the n plus 1 and divide by n plus 1. To cancel out the bringing down of the constant. It's the power rule in reverse. Instead of bringing down the constant, you divide by the constant. And then you can always add plus a c to it. This is all good and dandy as long as n is not -1. Because you'll be divided by 0. So this works for everything except when you have x to the -1. If your function is x to the -1, you can't use this reverse power rule. Because you'll be divided by 0. We'll come back to x to the -1. We know how to take the antiderivative of that. We just have to remember. But for now, as it stands, we just can't do it. Not with this reverse power rule. All right. So if you have x to the 4th as your derivative, the function will be x to the 5th. But to balance out the 5 that you would bring down, you have to divide by 5. And always you can add a constant at the end. If you have a bunch of terms added together, you can do each term individually. If there's constants in front, just like with the derivative, you carry the constant. With the antiderivative, just carry the constant. Leave the 3 there. Take x cubed and divide it by 3. Leave the 2 there. take x to the fourth and divide it by 4. And as far as negative 5 is concerned, it's just like the 8. Attach on an x. And then always at the end, add a c. Forgetting to do that will cost you a point. And then you simplify, of course. The 3's cancel. This 2 turns the 4 into a 2. So the function that has that polynomial as its derivative is x cubed plus half of x fourth minus 5x plus a constant. So we're working backwards. We have a derivative and we want to find the function. We're starting off simple with the polynomials, and then we'll get more difficult when we go with the trig and the exponentials and the logs. And the arc sine, it's arc cosine and arc tan, the inverse trig. Questions on the first slide? All right. Let me get rid of this here. How about trig? Sine x minus 3 times the secant squared on x. When you look at this, you're trying to say, what function has this as its derivative? What function has sine, positive, sine as its derivative? You got to put a negative on the cosine. So that when you bring the negative from cosine's derivative, it cancels with the negative to give you a positive sine of x. Great. What function has secant squared as its derivative? Tangent. So we're doing each part individually. And the constant that's in front, the negative 3, just carry that down. So you'll have a negative cosine of x for the first part, and negative 3 tan x for the second term. Only because we recognize it. Had it been any other, had it been sine squared, we don't know how to get the antiderivative of that right away. We'll need some techniques to do that. But we recognize sine as cosine's derivative with a negative on there. We recognize secant squared as tan's derivative. So as long as it's something that we recognize, we can just report what the antiderivative is. But what if you have radicals and things that are on the denominator? So root x, and then the x squared, and then the 1 over x squared. It's not like you have to do a quotient rule in reverse. It doesn't work like that. So that reverse power rule works no matter what the n is except for -1. It works for fractions. It works for negatives. So that radical is just an x to the half. That x to the x squared on the bottom is really an x to the -2. So rewrite your function and then do the reverse power rule on it. Add 1 to the exponent, divide by exactly the same thing. So if you add a half and you add 1, where are you? 1/2 plus 1? 3 halves. Very good. Now you're supposed to divide by the same thing. Divide by 3 halves. Well, instead of dividing by a fraction, let's multiply by the reciprocal. So we divide by 3 halves, yeah, but we're going to call it 2/3 multiplied by. The middle term is just like we saw from the last slide. X squared is x cubed over 3 as the function that has x squared as its derivative. And then when it comes to this guy, the -2, if you're at -2 and you add 1, you're at -1. That's your new exponent. That's your new thing that you're dividing by. Why is there a minus here? Only because there was a minus here. Just make sure your exponent matches what you're dividing by. And then later simplify. Make sure the signs in between matches the signs in between. If there's constants, just carry them down. So instead of divide by 3 halves, we'll multiply by 2/3. Instead of having a -1, we'll have a plus. And we'll put the x back on the denominator. That's the function that has root x plus x squared minus 1 over x squared as its derivative. power rule in reverse. Even when it's radical. What if it's the cube root? It's no different. Just make it a fraction. You got to know that the cube root is x to the third. Students really get tripped up when I give them this. The exponent on the fourth root is 1/4. It's already cubed. And then it's to the fourth. So it's x to the 3/4. Very good. You got to be able to do that. I'll give you the symbol. I won't give you the fractional exponent. I'll ask you for the antiderivative. You'll have to do the algebra to figure out what the right antiderivative is, and then do the power rule in reverse on it. Okay? If you see the square root of x to the 7th, that's not x to the 1/7. It's not the 7th root. The exponent is 7/2. Don't let the algebra stop you from being able to get the problem right. Okay? Algebra sometimes is a hindrance to you, and it shouldn't be. Now, what we're saying is that I can add any constant I want. So technically, there's infinitely many. If you think of the graph of a function, and then you add a constant to it, what that does is shift the function up or down. So technically, there are infinitely many curves based on the infinitely many constants. There's infinitely many curves that will be that would have this function as its derivative. If you want to know, not the infinitely many, but if you want to know exactly one curve, what you do is you're given a point. If you give a point that the function must go through, then you'll go from infinitely many curves to exactly one curve. What that will do will help you be able to solve for exactly what C is. So, if you're told that when you plug in 4, you get a 30 out, only one of these infinitely many functions will go through that point. So, what we're doing is we're pairing it up. I say, I want the function. Basically, the question is this. Find the function. There's only one, so we can say the. That has a derivative of, let's go with the same problem. F prime of x is root x plus x squared minus 1 over x squared. And basically goes through the point 430. Right? This statement here, this symbol, can be written as a point. We've done the work. We know all functions that have this guy as their derivative, but we want the exact function that has the quality that it goes through 430. When x is 4, y is 30. That's how you translate that. Okay, so we're looking at f of x being equal to 2x to the 3/2 over 3, x to the 3 over 3, 1 over x plus a c. That's the f of x. But if you want to call it y, you can. When I plug in x equals 4, you should get out y equals 30. The only mystery then will be what the c is. So can you do it? Take f of 4, 30, which is equal to f of 4, is 2 times 4 to the 3/2 over 3, 4 to the 3 over 3, 1 over 4 plus a c. Your job is to do some algebra. Find the c. Don't make a mistake and multiply the 2 and 4 together. PEMDAS. Exponents come from multiplication. Raise 4 to the 3/2 power. How do you raise 4 to the 3/2 power? Without a calculator. You raise 4 to the 1/2 power, and then you cube it. Because 4 to the 1/2 power is the square root of 4, which is 2. So it's 2 cubed, so it's 8. Great. This in disguise is an 8. Now go do the rest of it. I know it's fraction addition. You can do it though. 16/3. What is 4 cubed? 64. So you're looking at 16/3 plus 64/3. Let's go ahead and put those together, since they have the same denominator. 80/3. Okay, 80/3. Wonderful. So I'm done with all this. I have 80/3. What else is there? A fourth, a C, and it's equal to 30. Take 80/3 and add a fourth. How do you do that? Common denominator between 3 and 4? 12. Both of these need to be over 12. Can't go grab a calculator on your own. No crutch. So you multiply the first fraction by 4, top and bottom. Second fraction by 3, top and bottom. What does that become? It becomes 320. That's what 80 times 4 is. 320, and then add on 3. All right, it's getting messy, but so what? 323 over 12. All right, great. This is kind of like scratch work. We're at this point, and now we know that we have 323 over 3 plus a C should be 30. We need to solve for C. Just checking, just checking. That was on purpose. That was on purpose. So what's C? Well, how do you find C? Let's just say that. Subtract over that 323 over 12. So C is 30 minus 323 over 12. 30 times 12 is 360. When you subtract 323 from 360, you get 37. C is 37 over 12. The function that's the solution to this problem is exactly that. Okay. And this is what we'll have to do for next chapter. We're just getting ready. This is just warm up. The rest of calculus is this antiderivative, working backwards. What about if you have a second derivative? And you want the function. You do it once to get the derivative. You do it again to get the original function. Antiderivative once gets you f prime. Antiderivative again gets you f. The good thing about it is that it's a polynomial. So we just power rule in reverse. You do it once, and let's say we know these facts. That when when you plug a 0 in, you get a 2, and when you plug a 1 in, you get a 0. These are facts that we need to know to nail it down from being infinitely many solutions to exactly one solution. This comes at the end. This is like what we use to solve for C. Okay, so first up, antiderivative. You tell me, talk me through it. What is the antiderivative of this particular polynomial? Call it f prime. Leave the 2, x to the 4th over 4. We can simplify it later and call it half of x to the 4th. Leave the 3, call it x cubed over 3. Simplify it later and call it x cubed. Leave the negative 4, go x squared over 2. Simplify later, call it 2x squared. Leave the 5, tack on an x. Tack on a c. Add it on. You've done it. That's the antiderivative once. Let's simplify it. Some of you on the exam, you tried to go and do a second derivative before you simplify the first derivative. It made your life harder. Let's simplify this before we do it again. We get x 4th over 2 plus x cubed minus 2x squared plus 5x plus c. That's the derivative, though, not the function. We can't use this information because this information is not about the derivative. This information is about the function. So we need to do it again. Antiderivative of f prime is f. So we do it again. And we call it f of x. Leave the half. And do it as x 5th over 5. X 4th over 4. Leave the negative 2 and do it as x 3 over 3. Leave the 5 and do it as x squared over 2. Now, this is a constant, like our 8. Antiderivative of 8 was 8x. Antiderivative of c, cx. Now we have to add another constant. Let's not call it c. Okay, sounds great to me. This is your function. Good job. Simplify it, and let's go find the c and the d. Simplify it how? Well, you know, this x to the 5th over 5 and the half. Let's call that x to the 5th over 10. Let's call this one 2x cubed over 3. 5x squared all over 2. Making it as simple as possible before we start plugging stuff in. That's your answer, but we just need the C and the D. 8 points out of 10. It's great. Good job. But you want full credit. Let's take this one. This one actually is the best one to start with. When f has a 0 plugged into it, a 2 comes out. We love plugging zeros into polynomials. Why? You just get the constant. All of that zeros out. You just get D. In disguise, this is telling us that D is 2. F of 0 equals D. All right, so we know D. Great, 9 points out of 10. Wonderful. Let's go get C using this other piece of information. Now that we know that D is 2, when we plug a 1 in, we'll get a 10th. We add a 4th. We take away 2/3. We add on 5 halves. We love plugging 1s into polynomials too. You just get coefficients. Then we get C, and then we get D, because D is 2, so we just say plus a 2. And this is supposed to be 0. So we set it equal to 0, and we solve for C. Here we go again, all this fraction arithmetic. 10, 4, 3, 2. Common denominator. You could go 120, but you could do better. 60. The least common denominator. Put everybody over 60. Times this guy by 6. Times this guy by 15. Times this guy by 20. Times this guy by 30. This is really 2 over 1, so times it by 60. Gotta make it fun because it's ridiculous. 6 plus 15 plus 40 plus 150 plus 120 all over 60 plus a C is nothing. Oh, there was a minus in there? Oh, that was on purpose. That was on purpose. That was on purpose. Just check it. Just check it. Okay. All right, who's all the positive? 150, 120, 21. I don't know, what's that? 391. Take away 40. Whatever. That's what it is. 351 over 60. C is the negative of that. And you're done. Rewrite your answer as this entire polynomial with the C and the D plugged in. Question, yes? Sure, that works. Just checking, just checking, just checking. See if you're paying attention. Good job. Good catch. Extra points for people that catch the mistakes. 251. Okay, that's enough. There's one more that we could do, but that's enough for today. Have a good weekend. See you at the game on Friday. Battle of 33rd Street. They've lost 2 games. They're hungry. They're going to try to kill us.